So, here is something worth thinking about as you settle in tonight, in the quiet, in the dark, as the room grows still around you. Out there, across a distance so vast the mind cannot hold it, there may be a single structure so enormous that it should not, by our best understanding, be able to exist at all. It is a wall of galaxies. Not one galaxy, not 100, but many billions of them, strung together across a span of the universe so wide that light itself would take billions of years to cross it. It has a long and awkward name, the Hercules Borealis Great Wall. And tonight, we are going to travel all the way out to it, slowly, gently, and try to understand what it is and why it troubles the people who study the universe. You do not need to stay awake for any of it. Let us say the size once, softly, and then set it aside, because it will not mean much yet. This wall of galaxies may stretch across something like 10 billion light years. 10 billion. That means light, the fastest thing there is, would need 10 billion years simply to travel from one end of it to the other. To put that in some kind of scale, the entire observable universe is only about 93 billion light years across. So this single structure, if the measurements are right, may span a good fraction of everything we can see. It is not a large thing in the universe. It may be one of the largest things the universe contains, full stop. And that, as we will see, is exactly the problem. It helps to sit with that word, problem, because it is not the word you might expect. Finding the largest thing ever should be a triumph, a record, something to celebrate. And in a way, it is. But it is also a worry. Why would a discovery be a worry? Because this one may be too big to fit our rules. The universe is supposed to have a size limit for its structures, a ceiling, nothing much bigger than about 1 billion light years across. And this wall may be 10 billion or more. So it does not just break the record, it breaks the ceiling. It sits, if it is real, in a place our theories say should be empty of such things. That is why the people who study it are uneasy as well as delighted. They have found something wonderful, and it should not be there. Both of those are true at once. Hold them together. That tension is the whole heart of tonight. This is a story about that bigness, and about a quiet crisis it may cause, and about the honest, careful, unfinished argument over whether it is even real. Because here is the thing worth holding on to as you drift. For most of the last century, cosmologists have built their understanding of the universe on a simple and beautiful assumption. The assumption is that the universe, on the largest scales, is smooth. That if you zoom far enough out, one big patch of the cosmos looks much like any other, with no enormous structures, no giant walls, nothing too big. This wall of galaxies, if it is truly there, may be too big for that assumption to hold. It may be a structure that our rules say should not exist. And so it sits out there, at the edge of what we can measure, a quiet challenge to some of our deepest ideas about the shape of everything. You do not need to follow every step of it. You do not need to hold the numbers, or the names, or the distances. If you drift off somewhere out among the galaxies, that is perfectly fine. The Great Wall, whatever it truly is, will go on being exactly what it is, whether or not you are listening, as it has for billions of years, without ever once needing your attention. The point tonight is not to learn. The point is to rest, and to let your mind wander gently out across the vast web of the universe, out to the largest thing we have ever glimpsed, and to feel, in a calm and unhurried way, just how small and safe and quiet you are, here, in your bed, a single warm point of life within a structure beyond all imagining. Let us begin, though, not with the Great Wall itself, but with a simpler and more beautiful idea underneath it. The idea that the universe is not scattered at random. Because to understand why a wall of galaxies is so strange, you first have to understand how galaxies are actually arranged across the cosmos, and the answer is one of the loveliest discoveries of the last 100 years. The universe, it turns out, has a structure. It has a shape. The galaxies are not sprinkled evenly through space like sand. They are gathered and strung and woven into a vast and delicate pattern, one that took us a very long time to see, and that looks, when you finally map it, astonishingly like something alive. Let that idea land gently, because it changes how you see the night sky. We look up and see stars scattered about, seemingly at random, and for a long time we thought the galaxies were like that too, just sprinkled through space. Here one, there another. No pattern. But there is a pattern, a deep one. Ask yourself, if galaxies are pulled together by gravity over billions of years, what would happen? They would gather. They would clump. They would drift toward one another and gather into groups, and the groups would gather into larger groups, and so on and on, for the whole age of the universe. That is exactly what happened. Nothing stayed evenly spread. Everything was drawn together into threads and knots and walls. The even sprinkle became a web, and it took us most of a century just to see it. Picture a single galaxy first, to start small. Our own Milky Way is a great spiral of a few 100 billion stars, turning slowly in the dark, a vast island of light. It is enormous. Light takes about 100,000 years just to cross it. And for a long time, people imagined that galaxies like ours were simply scattered here and there through space, more or less evenly, like stars scattered across the night sky. But that is not how it is. Galaxies are social. They gather together. Our Milky Way is not alone. It belongs to a small cluster of galaxies we call the local group, bound together by gravity, drifting through space as a family. And the local group, in turn, is part of something larger. It sits near the edge of a much greater collection of galaxies, thousands of them, called the Virgo supercluster, or sometimes, in a newer and grander mapping, part of an even vaster flow of galaxies, given the name Laniakea, a word from Hawaiian meaning immeasurable heaven. So it goes, at every scale. Galaxies gather into groups. Groups gather into clusters. Clusters gather into superclusters. Nothing, it seems, is truly alone. At every level, gravity has been quietly pulling things together for billions of years, building larger and larger gatherings out of smaller ones. It is worth pausing on how patient that building has been. Gravity is not strong. It is the weakest force there is. A small magnet can beat the whole pull of the Earth. So how did it build the largest things in the universe? Time. Endless time. Gravity never rests, and it never stops, and it always pulls. Give it 1 billion years, and then another, and its gentle, ceaseless tug adds up. Grain by grain. Galaxy by galaxy. It gathered the stars into galaxies. It gathered the galaxies into groups. It gathered the groups into clusters, and the clusters into the great web. All of it, by the same faint force that returns a tossed ball to your hand. Is that not a strange thought? The largest structures there are were built by the weakest force there is, given nothing but time. And there was so very much time. But the real surprise is what those gatherings look like when you map them across truly enormous distances. Because the clusters and superclusters are not just blobs scattered here and there. They are connected. They are strung together along vast threads into a single connected pattern that spans the entire visible universe. Astronomers call it the cosmic web, and the name is exactly right. If you could stand outside the universe and look at how all its galaxies are arranged, you would not see an even sprinkle. You would see something that looks like a web, or like foam, or like the branching threads of a great neural network. Long, bright filaments of galaxies, stretching for hundreds of millions of light years. Dense knots where the filaments cross, glowing with clusters. And between them, enormous dark and nearly empty spaces, called voids, where there is almost nothing at all. Let that image settle, because it is one of the most beautiful in all of science. The universe, on the largest scales, is mostly empty. The galaxies are gathered onto thin, bright walls and threads, wrapped around vast bubbles of emptiness, like the soap film in a great mass of bubbles, or like a sponge, all surface and hollow. The bright places, where the galaxies live, are the walls of the bubbles. The dark places, the voids, are the insides of the bubbles, immense rounded regions of near nothing, tens or hundreds of millions of light years across, with only a stray galaxy or two drifting through all that emptiness. We live on one of the bright threads. Everything we can see, every galaxy in every direction, is part of this single vast foam. Sit with the voids for a moment, because they are as wonderful as the walls. We talk about the galaxies, the bright threads, the crowded places, but most of the universe is not that. Most of it is void, empty, vast rounded hollows, hundreds of millions of light years wide, with almost nothing inside. If you were placed at the center of a great void, what would you see? Almost nothing. A few faint galaxies, impossibly far. Otherwise, dark in every direction, for further than the mind can hold. There are places in the universe that lonely. And they are not rare. They are most of it. The bright web we marvel at is really just the thin skin around the emptiness, the foam around the bubbles. The universe is mostly hollow, and we are lucky enough to live on one of its bright and crowded threads, where there are stars and warmth and neighbors in the sky. And this pattern is not an accident. It is a fossil. It is the frozen record of the very early universe, grown enormous. In the first moments after the beginning, the universe was almost perfectly smooth, but not quite. There were tiny ripples in it, faint patches that were a little denser than average, and other patches a little thinner. And over billions of years, gravity took those tiny differences and grew them. The slightly denser patches pulled in more matter, growing denser still, while the thinner patches gave up their matter and grew emptier. The dense regions became the filaments and the walls and the clusters. The thin regions became the voids. The cosmic web we see today is those first tiny ripples, amplified by billions of years of gravity, written across the whole sky. When you look at the great web, you are looking at the shape of the newborn universe, grown up. Let that connection settle slowly, because it is one of the deepest in all of science. The web is old, older than it looks. Its shape was set in the first moments after the beginning. Back then, the universe was almost perfectly smooth. Almost, but not quite. There were tiny ripples in it, faint patches, a little denser than the rest. Where did they come from? From the quantum flicker of the very early universe, blown up to cosmic size in the first instant. Impossibly small differences, frozen into the newborn cosmos. And then gravity went to work on them. The denser patches pulled in more. The thinner patches gave up what they had. Over billions of years, the tiny ripples grew into the walls and the voids. So the web is a fossil, a baby picture, grown enormous. When you map it, you are seeing the shape of the universe as it was in its very first moment, written across the whole of the sky. Now here's the question that leads us slowly toward the Great Wall. How big can these structures get? The web has filaments and walls and clusters at many scales, from small to large. But is there a limit? Is there a largest size beyond which structures simply do not form? For a long time, this was more of an assumption than a measurement, and it rested on that deep idea we mentioned, the one at the heart of cosmology, which we will come to properly in a while. For now, hold the gentle question in mind. There is a web. It has bright walls and threads of galaxies, and we would like to know how large the largest of those walls can be. To answer that, we first had to learn to map the web, and that turned out to be one of the great adventures of modern astronomy. Mapping the web is harder than it sounds, and understanding why is worth a slow moment, because it explains how we came to find the great walls at all. When you look up at the night sky, you see the stars and galaxies flattened onto a kind of dome. You can see where each one sits, left or right, up or down. But you cannot easily see how far away each one is. The sky looks two-dimensional, a flat scattering of lights, with all the depth pressed out of it. Two galaxies that appear right next to each other might in truth be billions of light years apart, one far behind the other. To map the cosmic web, to see its true three-dimensional shape, you need to know not just where each galaxy sits on the sky, but how far away it is. And measuring the distance to a galaxy is one of the hardest things in astronomy. The key, once again, is redshift, the same tool that unmasked the quasars. Because the universe is expanding, distant galaxies are all moving away from us, and the further away a galaxy is, the faster it recedes, and that motion stretches its light toward the red by an amount we can measure. So the redshift of a galaxy tells us its speed of recession, and its speed tells us, roughly, its distance. Measure the redshift of a galaxy, and you have placed it not just on the flat dome of the sky, but at a real depth, a real distance, in three-dimensional space. Do that for one galaxy, and you have a single point. Do it for thousands, and then millions, and slowly, painstakingly, the flat scattering of lights lifts off the dome and becomes a true map with depth and shape and structure. The web appears. Think about how strange and hard that is to do. Look up at the sky. What do you see? A flat dome, lights painted on a ceiling. You cannot tell what is near and what is far. Two galaxies side by side might be neighbors, or one might be far behind the other. How could you ever know? For most of history, we could not. The depth was simply hidden. And then came the trick. Redshift, the stretch of light from things rushing away. The farther a galaxy, the faster it flees, and the more its light is stretched. Measure that stretch, and you know the distance. Suddenly the flat dome gains depth. Each galaxy lifts off the ceiling and takes its true place in space. Do it once, and you have a dot. Do it 1,000,000 times, and the whole web appears, rising out of the flatness like a shape out of fog. That is how we learned the true form of the universe, one stretched color at a time. The first person to map the web this way, on a large scale, and to be truly shocked by what she found, was an astronomer named Margaret Geller, working with her colleague John Huchra in the 1980s. They set out to measure the redshifts, and so the distances, of thousands of galaxies in one slice of the sky, patiently, one galaxy at a time, over years. It was slow and unglamorous work. But when they plotted the results, when they finally drew the map of where all those galaxies really were in 3 dimensions, they saw something no one had quite expected. The galaxies were not spread out evenly at all. They were arranged in thin, curving structures, wrapped around great empty voids, like a slice through a mass of soap bubbles. And running across their map was a single enormous structure, a long, thin concentration of galaxies stretching across a huge span of their survey. They called it the Great Wall. It was, at the time, the largest known structure in the universe, a sheet of galaxies more than 500 million light-years long. People were astonished that anything so large could exist, and there was a lovely, human detail in that first map. In one region, the arrangement of galaxies happened to look, to the eye, a little like a stick figure of a running person, arms and legs outstretched, and the astronomers affectionately called it the stick man. The universe, mapped for the first time in real depth, had turned out to be full of structure, and even, if you squinted, of shapes. It is worth savoring how surprising that first map was. Geller and Hukra were not expecting a wall. No one was. The gentle assumption was that galaxies would be spread fairly evenly, once you mapped enough of them, a smooth scatter, and instead, thin curving sheets, great empty bubbles, a single enormous wall of galaxies running clear across the survey. Was it a mistake at first? They checked. It held. The universe really was built this way, in walls and voids, not in an even sprinkle. Imagine being the first person to see that, to plot your thousands of hard-won dots and watch a structure appear that no one had ever known was there. That is one of the quiet thrills of science, not the thrill of proving what you expected, the thrill of finding what you did not expect at all, waiting in your own careful data, the true shape of the universe showing itself for the first time. That first Great Wall was only the beginning. As telescopes improved and as astronomers built great automated surveys that could measure the redshifts not of thousands of galaxies, but of millions, the maps grew deeper and wider, and larger structures came into view. The most famous of these surveys is called the Sloan Digital Sky Survey, which patiently mapped the positions and distances of many millions of galaxies across a huge portion of the sky, building the most detailed 3-dimensional map of the universe ever made. And in that map, an even larger structure appeared, a concentration of galaxies given the name the Sloan Great Wall, stretching across something like 1.5 billion light-years, nearly 3 times longer than the first Great Wall that had so astonished everyone a couple of decades before. Each time, the pattern was the same. A new survey would map more of the universe, and a new largest structure would appear, bigger than the last. And each time, there was a quiet question lurking behind the wonder. How big is too big? Because, as we have hinted, there is supposed to be a limit. There is supposed to be a size beyond which structures simply cannot form, a scale on which the universe is supposed to become smooth and featureless. And with each new giant wall, astronomers found themselves edging closer to that supposed limit, and beginning to wonder what would happen if something ever crossed it. To understand that limit, and why crossing it would matter so much, we need to look at the quiet assumption it rests on, one of the deepest ideas in all of cosmology. The idea is called the cosmological principle, and it is beautiful in its simplicity. It says, in essence, that the universe is the same everywhere and looks the same in every direction once you zoom out far enough. That there is nothing special about our location, no center, no edge, no privileged place. that a very large patch of the universe here looks, on average, just like a very large patch of the universe anywhere else. Smooth, uniform, the same in all directions and all places, on the largest scales. It is sometimes summed up in two long words. The universe is homogeneous, meaning the same in every place, and isotropic, meaning the same in every direction. Why do cosmologists believe this? Partly out of a kind of humility. For most of history, human beings assumed they were at the center of everything, and every time we looked closer, we found we were not. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. The galaxy is not the center of the universe. The cosmological principle takes that hard-learned lesson to its logical end and says, let us assume there is no center at all, that we are nowhere special, that the universe is fundamentally the same everywhere. And partly, they believe it because it works. The whole modern science of cosmology, our entire understanding of the expanding universe, the Big Bang, the ages and distances of things, is built on the mathematics that the cosmological principle makes possible. Assume the universe is smooth on large scales, and the equations become solvable, and their answers match what we see again and again. It is one of the most successful assumptions in the history of science. It is worth being clear about why this assumption matters so much, because the whole tension of tonight rests on it. Why assume the universe is smooth? 2 reasons. First, humility. Every time we thought we were special, at the center, we were wrong. The Earth is not the center. The Sun is not. Our galaxy is not. So we assume at last that nowhere is special, that the universe is the same everywhere. Second, it works. Assume smoothness, and the equations of cosmology can be solved. The expansion, the age, the distances, all of it falls into place and matches what we see. So the assumption has earned its place. But here is the catch. It only holds if there are no structures that are too big, too large a structure, and one region is no longer like another, and the smoothness breaks. So how big is too big? That question is where the Great Wall walks in. But here is the crucial part, the part that leads straight to our Great Wall. The cosmological principle does not say the universe is smooth on all scales. Of course, it is lumpy on small scales. There are planets and stars and galaxies and clusters, and even the great walls we have been describing. The principle says only that if you zoom out far enough, past all of that lumpiness, the universe eventually becomes smooth. There is supposed to be a scale, a certain enormous size, beyond which you no longer find bigger and bigger structures, beyond which every giant region looks like every other. Astronomers have a rough figure for that scale, the size beyond which the universe should look smooth. It is often put at somewhere around 1 billion light years, or a little more, perhaps 1.25 billion. Structures smaller than that are expected, and fine. Structures much larger than that should not exist. If they did, it would mean the universe is not smooth even on the largest scales, and the cosmological principle, that deep and load-bearing assumption, would be in trouble. So hold those 2 numbers gently in your mind, side by side, because the whole tension of tonight lives in the gap between them. On one side, the limit. Structures should not be much bigger than about 1.25 billion light years. On the other side, the Great Wall we are traveling toward, which may stretch across something like 10 billion light years, not a little over the limit, many times over it. If it is real, it is not just a record breaker. It is a structure so far beyond what the rules allow that it calls the rules themselves into question. And that is why a wall of galaxies, out at the edge of the visible universe, has quietly become one of the most interesting and troubling objects in all of cosmology. To find a structure that vast, out at the edge of the visible universe, ordinary galaxy surveys are not enough. Even the great surveys that mapped millions of galaxies reach only so deep. The faint, distant galaxies at the far edge of the cosmos are simply too dim to measure one by one across the whole sky. So to probe the truly deep universe, astronomers needed a different kind of marker, something bright enough to be seen across almost the entire observable cosmos. And it turned out there was such a thing, though it is one of the strangest and most violent events in all of nature. Gamma-ray bursts. A gamma-ray burst is, for the brief moment it lasts, the brightest explosion in the universe. It is a sudden, ferocious flash of the most energetic light there is, gamma rays, released in seconds or minutes, and in that short time, a single burst can outshine everything else in the sky combined. They come from the deaths of the most massive stars, and from the collisions of the dead remnants of stars, catastrophic events that, for a few seconds, pour out more energy than the sun will release in its entire 10 billion year lifetime. They are so bright that we can see them from across almost the whole universe, from distances so great that ordinary galaxies would be far too faint to detect. Each burst is a brief, brilliant beacon, marking the spot where a star died, billions of light years away. Let the strangeness of that tool sink in. To map the deepest universe, we use death, the death of the largest stars. When a giant star dies, or when two dead stars collide, there is a flash, a gamma-ray burst, and for a few seconds, that one flash outshines everything. How bright is it really? In seconds, it can pour out more energy than the sun will give in its entire 10 billion year life. All at once, in a flash. That is why we can see them from across nearly the whole universe, when ordinary galaxies at that distance are far too faint to spot. So each burst is a flare, fired off in the deep dark, marking a place where a star has died. And where a star died, a galaxy lives. Map the flares, and you map the galaxies, out to depths nothing else can reach. We chart the living universe by the light of its dying stars. Is that not a strange and beautiful way to make a map? And that is what makes them useful for our story. Because a gamma-ray burst marks the location of a galaxy, the galaxy where that dying star lived. Most gamma-ray bursts happen in galaxies, and so, if you map where the bursts occur across the sky and at what distances, you are, in a rough way, mapping where the galaxies are, out to enormous depths that ordinary surveys cannot reach. The bursts are like scattered flares fired off across the deep universe, each one lighting up, for an instant, a place where matter has gathered into a galaxy. Collect enough of them, note their positions and their distances, and you have a crude map of the distribution of matter in the deep cosmos, far beyond where you could ever map individual galaxies. There is a catch, and it is an important one that we will return to when we come to the doubts. Gamma-ray bursts are rare, and they are scattered thinly, so any map made from them is coarse and patchy compared to a proper galaxy survey. You are not seeing every galaxy, only the rare few that happen to host a burst during the years you are watching. It is like trying to map a great city at night by watching only the occasional firework, noting where each one goes off. You would get a rough sense of where the crowds are, where things are happening, but it would be a blurry, incomplete picture, easy to misread. Keep that image in mind. It matters later, when we ask whether the Great Wall is truly there. Let us hold that firework image a little longer, because it is the key to the whole doubt. Imagine you want to map a dark city. You cannot see the streets. You cannot see the houses. All you can see is the occasional firework going off here and there over the hours. Where the fireworks cluster, you guess there are crowds. Where they are sparse, you guess it is quiet. Would your map be good? Roughly, maybe, but full of holes. A place with a big celebration and no fireworks would look empty. A few fireworks that happened to go off near each other, by pure chance, would look like a crowd that was not there. That is the trouble with mapping by gamma-ray bursts. They are the fireworks, rare, scattered, and easy to misread. So when we see them cluster in one direction, we have to ask a hard question. Is that a real crowd of galaxies? Or just a chance run of fireworks going off near each other, meaning nothing? That question has no easy answer, and the whole reality of the Great Wall hangs on it. But for now, follow the discovery. In the early 2010s, a group of astronomers, led by a Hungarian researcher named István Horváth, along with his colleagues, were studying the distribution of gamma-ray bursts across the sky. They had a catalog of hundreds of bursts collected over years by orbiting telescopes, each with a measured position and a measured distance. And as they looked at how these bursts were spread across the deep universe, they noticed something odd. The bursts were not spread evenly. In one particular region of the sky, in the direction of the constellations Hercules and Corona Borealis, the northern crown, there was a clustering, an excess, far more gamma-ray bursts at a certain range of distances than you would expect if the universe were smooth out there. A clustering of gamma-ray bursts means a clustering of the galaxies that host them, which means a concentration of matter, a structure. And when they measured the extent of this clustering, the size of the region over which the bursts were gathered, the number was staggering. The structure appeared to stretch across something like 10 billion light-years. They had found, or seemed to have found, a concentration of matter larger than anything ever seen before, far larger, out in the direction of Hercules and the northern crown, and so it was given its long and stately name. The Hercules Corona Borealis Great Wall, the largest structure, if it is real, ever discovered in the universe. Say the name slowly, because it holds a small piece of the old sky. Hercules, Corona Borealis, the northern crown. These are constellations, patterns our ancestors drew among the stars thousands of years ago, of a hero and a crown. The Great Wall lies in that direction, far beyond those stars, billions of light years past them. But we named it for them anyway, for the old figures in the near sky that happen to point the way. There is something lovely in that. The largest structure in the universe, so new and so strange we are still arguing whether it exists, carries the name of a hero the ancient Greeks drew in the stars. The oldest names, pointing at the newest and largest thing. And in that direction, if the data can be trusted, the galaxies gather more thickly than they should, across a span so vast the mind lets go of it. In the direction of the hero and the crown, something is out there, or seems to be. Let that discovery settle for a moment, gently, because it is a strange and quiet kind of finding. No one saw the wall directly. No telescope made a picture of 10 billion light-years of galaxies strung together. What the astronomers found was a pattern in the deaths of stars, an unexpected crowding of the brightest explosions in the universe, in one direction, at one range of distances. From that crowding, they inferred a structure. It is an indirect discovery, built on a chain of reasoning, much like the way we weigh a black hole we cannot see. And like any indirect discovery, it comes with real uncertainty, which is exactly why it has been argued over ever since. But the pattern was there in the data. In the direction of Hercules, something seemed to be gathered on a scale that should not be possible, and the size only grew. In the years after the first announcement, astronomers continued to study the region, gathering more gamma-ray bursts, refining the measurements. And some of that later work suggested the structure might be even larger than first thought, and closer to us than first believed. Certain analyses put its span at not 10, but many billions of light-years across, a good fraction of the entire observable universe, a structure so vast that the words we use for size begin to lose their footing. Let us be honest about what happens to the mind at these sizes. It stops working. It simply cannot picture them. 10 billion light-years, 30 billion, a third of everything there is to see. These are not sizes you can hold. You can hold a room, maybe a city, with effort, a planet. But this? No. And that is worth saying plainly, because it is not a failure on your part. It is the correct response. The mind evolved to judge distances you could walk or throw a stone across. It was never built for this. So do not strain to picture the Great Wall to scale. You cannot, and neither can anyone. Just let the words wash over you. Vast, enormous, a good fraction of everything. Let them be feelings rather than pictures. The awe is real, even when the image will not come. In fact, the awe is strongest exactly where the image fails. That soft giving way of the mind, reaching for a size too large to hold, is itself the point. Rest in it. Whether those larger figures are right is part of the ongoing debate. But at every step, the Great Wall in Hercules has remained stubbornly, troublingly enormous, far larger than the limit the cosmological principle seems to allow. It has refused, so far, to shrink into something comfortable. And that refusal is exactly what makes it interesting. Think about it. If the wall were just a little over the limit, we could shrug. Measurements are imperfect. A little too big is easy to forgive. But the Great Wall is not a little too big. It is many times too big. 8 times the limit at least. Perhaps far more. How do you shrug that off? You cannot, easily. Either the measurement is badly wrong, in some way we have not yet found, or the rule is wrong, or at least incomplete. There is not much comfortable middle ground. That is why it will not go away quietly. A small anomaly can be ignored. A giant one demands an answer. And the Great Wall, if it is real, is about as giant an anomaly as cosmology has. So it sits there, at the edge of the data, refusing to shrink, quietly insisting that we look again. Let us sit, gently, with why the size is such a problem, because it is the heart of the whole story, and it is a lovely thing to turn over slowly in the dark. Remember the 2 numbers. The cosmological principle says the universe should be smooth on scales larger than about 1.25 billion light-years. The Great Wall may span 10 billion light-years, or more. That is not a small disagreement. It is a structure roughly 8 times larger than the largest thing the rules are supposed to allow, and perhaps far more than that, if the bigger estimates hold. To feel why that matters, think again about what the cosmological principle really claims. It claims that if you take a box of the universe about 1 billion light-years across, and then take another such box somewhere else, they will look, on average, the same. Same number of galaxies, same density, no box dramatically different from any other. That sameness is what makes cosmology possible. It is the assumption that lets us treat the universe as a single, uniform thing, with one age, one rate of expansion, one history, describable by a single set of equations. Take away that sameness, allow enormous structures that make one region very different from another, and the beautiful simplicity begins to crack. A structure 10 billion light-years across is a region that is not like its neighbors. It is a vast patch of the universe with far more matter gathered into it than the average, on a scale where everything was supposed to have smoothed out. If it is truly there, then the universe is not smooth even on the largest scales we can measure. There is no size at which the lumpiness stops. And that would mean the cosmological principle, that deep and load-bearing assumption, is not quite true, or at least not true in the simple form we have relied on for a century. It would not necessarily overturn everything, but it would be a crack in the foundation, a sign that the universe is stranger and lumpier and less uniform than our tidiest theories require. You can see why this troubles cosmologists, and also why it fascinates them. No one wants their foundational assumption to be wrong, but everyone wants to be the one who finds the crack, the anomaly, the thing that does not fit, because that is where new understanding comes from. So the Great Wall in Hercules sits in a peculiar position. It is either a mistake, a mirage in patchy data, in which case it will eventually fade away and the principle will stand, or it is real, in which case it is one of the most important objects in cosmology, a genuine challenge to how we understand the shape of everything, and which of those it is has not yet been settled. That is what makes it such an honest and interesting story. We do not know the ending. There is something rare and refreshing in that, worth pausing on. So often, science is handed to us as finished facts. The Earth goes around the sun. Water is made of hydrogen and oxygen. Settled, done, memorize it. But this is different. This is science still in motion. Live, unfinished, argued over right now by people who genuinely do not agree. Is the Great Wall real? Some serious scientists say yes. Other serious scientists say no. Who is right? Nobody knows yet. And that is not a flaw in the story. It is the best part. You are not being told a settled fact tonight. You are being shown a real, open question at the very edge of human knowledge, still being worked out. Most of what we know was once a question exactly like this one, unsettled, argued over, uncertain. You are getting to watch the process itself, caught in the middle, before the answer arrives. That is a rare view and a privilege, even at the edge of sleep. So let us turn, carefully and fairly, to the doubts, because they are real, and a good scientist takes them seriously. There are strong reasons to wonder whether the Hercules Borealis Great Wall is truly a single structure at all, or whether it might be, at least in part, a trick of the way it was found. And the first and most important doubt comes straight back to that image of mapping a city by its fireworks. Remember, the wall was not found by mapping galaxies directly. It was found by mapping gamma-ray bursts, which are rare and scattered thinly, and which give only a coarse and patchy picture of where matter lies. When your data is sparse, patterns can appear that are not really there. If you scatter a handful of dots at random across a page, your eye, and even careful statistics, will sometimes find clumps and lines in them, clusters that look meaningful but arose purely by chance. With only a few hundred gamma-ray bursts spread across the entire sky and the entire depth of the universe, there is real room for a clustering to appear that is not a true structure, but simply a chance crowding in a small and noisy sample. Some astronomers have argued exactly this. They have taken the same kind of data, scattered at random, with no real structure at all, and found that clusters as large as the Great Wall can appear by chance often enough that the wall may not be statistically significant In other words, the pattern might be real, or it might be the cosmic equivalent of seeing a face in the clouds. There are other doubts too, more technical, but worth knowing in outline. Gamma-ray bursts are not perfectly even tracers of matter. They come from dying stars, and stars form more readily in some kinds of galaxies than others, so the bursts may not faithfully mark where all the matter is. The way the bursts are detected has its own biases, since our telescopes see some parts of the sky better than others and can measure some distances more easily than others. All of these effects can create apparent patterns that are really about how we are looking, not about what is truly out there. Untangling a real structure from all of these possible illusions in a sample of only a few hundred rare events is genuinely difficult, and reasonable scientists disagree about whether it has been done convincingly. It is worth admiring how careful this work has to be. A few hundred gamma-ray bursts, spread across the whole sky and the whole depth of the universe. That is not much to go on, and every one of them comes with its own quirks. Some parts of the sky are watched more closely than others. Some distances are easier to measure than others. Bursts come from dying stars, which favor some galaxies over others. Each of these things can bend the map. Each can make a pattern appear that is really about how we look, not about what is there. So how do you find a real structure in all that noise? Very, very carefully. You test it against random chance, again and again. You ask whether the clustering could have happened by luck. And honest people, doing this honestly, come to different answers. That is not sloppiness. It is the difficulty of the thing. Reading the deep universe from a few hundred distant deaths is genuinely hard, and no one should pretend otherwise. So where does that leave us? Honestly, it leaves us unsure, and that is the truthful answer, and not an unsatisfying one if you hold it the right way. The astronomers who found the Great Wall, and who have continued to study it, argue that the clustering is real, that it is too strong and too clear to be pure chance, and that we are seeing a genuine, enormous concentration of matter in the direction of Hercules. Other astronomers argue that the evidence is not yet strong enough, that the patchy data of gamma-ray bursts can fool us, and that the wall may shrink or dissolve as we gather more information. Both sides are being careful. Both sides are being honest. And the question remains open. The largest structure in the universe may be exactly that, or it may be a pattern we have read into the sparse light of dying stars. We do not yet know, and there is something rather beautiful in being able to say so plainly. Suppose for a while that it is real. Let us follow that possibility gently, because it is a fascinating one to drift on, and because the Great Wall is not entirely alone in raising the question. What would it mean for our understanding of the universe if there truly are structures this large? It would not mean that everything we know is wrong. The expanding universe would still be expanding. The Big Bang would still have happened. Galaxies would still form as they do. But it would mean that the universe is lumpier on the very largest scales than our simplest models allow, and that would send cosmologists back to their equations with a genuine puzzle to solve. One possibility is that our models of how structure grows are incomplete. We believe the cosmic web grew from tiny ripples in the early universe, amplified by gravity over billions of years. And our models are very good at reproducing the web we see, the filaments and voids and walls, up to a certain size. But if structures much larger than the models predict really exist, then perhaps there is something about the early universe, or about how gravity built the web, or about the mysterious dark matter and dark energy that shape it, that we do not yet fully understand. The Great Wall, if real, would be a clue, pointing at a gap in our knowledge, telling us that the universe assembled itself in a way our theories have not quite captured. Another possibility is subtler and turns on what we even mean by the word structure. When we call the Great Wall a structure, we might imagine a solid thing, a wall you could in principle walk along, all its galaxies bound together and moving as one. But a structure this large cannot possibly be bound together in that way. It is far too big. Gravity, over the age of the universe, has not had anywhere near enough time to pull galaxies together across 10 billion light years. So even if the Great Wall is a real concentration of matter, it is not a single object in the way a galaxy or a cluster is. It is more like a vast region that simply happens to hold more galaxies than average, a great crowd rather than a single body, its members not truly connected, only near one another, on a scale so large that light itself takes billions of years to cross from one side to the other. Part of the debate is really about what should count as a structure at all, at sizes this enormous. And here is a detail that keeps the question alive and makes it harder to dismiss the Great Wall as a simple fluke. It is not the only anomaly of its kind. Over the years, astronomers using gamma-ray bursts and other deep probes have reported several other structures that seem uncomfortably large, other patterns in the deep universe that strain against the cosmological principle. There have been reports of enormous rings of gamma-ray bursts and of vast groupings of quasars stretching across billions of light years, and of other great concentrations that, like the Hercules wall, seem to exceed the size the rules allow. Each one, on its own, might be explained away as a chance clustering in patchy data. But the fact that several such oversized structures keep turning up, in different surveys, using different methods, makes some astronomers wonder whether they are all really flukes, or whether the universe is quietly trying to tell us something. That is the deeper reason the Great Wall matters, beyond its own enormous size. It is part of a pattern of anomalies, a scattering of structures that all seem a little too big, all pushing gently against the same assumption. Any one of them might be noise, but taken together, they raise a real and open question about whether the universe is as smooth, on the largest scales, as we have long assumed. It may be that all of these apparent giants will eventually be explained, and the cosmological principle will stand, cleaner than ever. Or it may be that they are the first hints of a lumpier, stranger cosmos than we expected, and that 100 years from now, people will look back on the Great Wall and Hercules as one of the early clues that led to a deeper understanding. We cannot know yet which it will be. We are living inside the unfinished middle of the story. There is something worth pausing on in that, quite apart from the astronomy. It is a fine example of how science actually works, which is far messier and more honest than it is sometimes made to sound. There is no single dramatic experiment that settles the question. There is a patient gathering of sparse data and careful argument about what it means, and reasonable people disagreeing in good faith, and a slow, uneven movement toward the truth, with plenty of uncertainty along the way. The Great Wall is not a solved fact to be memorized. It is a live question being worked on right now by real people who do not yet know the answer. And there is something deeply reassuring in that, if you let it settle. The universe still holds open questions this large. The wondering is not finished. There is still, out there at the edge of what we can measure, a genuine mystery, patiently waiting. And whichever way it turns out, the Great Wall has already given us something valuable. It has pushed us to look harder at our deepest assumptions, to ask whether the smoothness we took for granted is really there, to build better surveys and gather more data and test the cosmological principle more carefully than we ever had before. Even if the wall itself eventually dissolves into noise, the questions it raised will have made our understanding of the universe sturdier, because an assumption that has been tested and survived is stronger than one that was never questioned at all. That is the quiet gift of an anomaly. It does not have to be right to be useful. It only has to make us look again. There is a deep lesson in that, worth carrying gently into sleep. We often think of being wrong as a failure, and we think a mystery is only worth something if it turns out to be true. But that is not how knowledge grows. Sometimes the most useful thing is a puzzle that makes us check our own assumptions. Was the Great Wall a mistake? Maybe. But even if it was, look at what it did. It made cosmologists ask, hard, whether the universe is really as smooth as they assumed. It made them build better surveys. It made them test the principle more carefully than ever before. Is that not valuable, whether or not the wall is real? A question that forces you to examine what you took for granted has already earned its keep. The Great Wall may or may not survive, but the looking it provoked has made our picture of the universe sturdier either way. Doubt, held honestly, is not the enemy of knowledge. It is how knowledge is made. Let us try gently to feel the scale of all this, because the numbers alone will slip through the mind, and there is a deep calm in reaching for sizes this large and letting them wash over you. Start with the observable universe, the whole of what we can, in principle, see. It is a sphere centered on us, not because we are special, but simply because we can only see out to the distance that light has had time to reach us since the beginning. That sphere is about 93 billion light-years across. Light, the fastest thing there is, would take far longer than the current age of the universe to cross it, because space itself has stretched while the light traveled. That is everything. Every galaxy we can ever see, all of it, within that sphere. Now place the Great Wall inside it. If the wall spans 10 billion light-years, then it reaches across more than 1/10 of the entire observable universe in a single structure. Hold that. Not 1/10 of the way to some nearby star, 1/10 of the way across everything there is to see, spanned by one concentration of galaxies. And if the larger estimates are right, if it truly reaches many billions of light-years further, then it may span 1/3 of the observable universe, or more, a fraction of the whole cosmos so large that it becomes almost meaningless to call it a structure within the universe, rather than simply a feature of the universe itself. This is why the size is so troubling and so magnificent. It is not large compared to a galaxy. It is large compared to everything, and you are inside it. That is the part worth sitting with, softly. We are not looking at the cosmic web from the outside, the way we look at a map. We are within it. Our galaxy sits on one of its bright threads, one filament among countless others, woven into the same great foam that holds the distant walls and voids. The Milky Way, and the local group, and the Virgo supercluster, and the vast flow of Laniakea are all part of the web, our own small strand of the enormous pattern. When you look up at the night sky, you are looking out from inside the web, along its threads and across its voids, at the other galaxies scattered on the same vast structure. We do not observe the cosmic web. We live in it. Let that turn your view inside out for a moment. We draw maps of the web as if we were looking at it from outside, as if it were a thing over there that we study from a distance, but we are not outside it. There is no outside. We are in it, on it, part of it. Our galaxy rides one of its bright threads woven into the pattern with all the rest. So when you look up, you are not looking at the web from beyond. You are looking out through it, from within, along its own strands. Every galaxy you can see is another part of the same structure you belong to. Does that make you feel small, or does it make you feel held? Both, perhaps. We are a tiny strand of something unimaginably vast, but we are a genuine part of it, not separate, not apart. The web runs through us. We are the universe's own structure, looking back at itself from the inside. There is a gentle vertigo in that, and also a gentle belonging. On the one hand, we are almost nothing, a single warm world, on a single ordinary star, on one thread of a web so large that a single one of its walls may span a tenth of everything. Set against that, our smallness is beyond words. But on the other hand, we are woven in. We are part of the pattern, not separate from it, not outside looking in, but a genuine strand of the same great structure that holds the farthest galaxies. The web runs through us, in a sense, all the way from the atoms in your body, forged in ancient stars, to the thread of galaxies our own rides upon. We are small, yes, but we are not apart. We are stitched into the largest pattern there is. It helps to trace that thread all the way down, gently, because it ends in you. The web is made of galaxies. The galaxies are made of stars. The stars are made of atoms. And the atoms in your own body, the iron in your blood, the calcium in your bones, the carbon in every cell, were forged inside stars long ago and scattered out when those stars died and gathered again into the cloud that became the sun and the earth and eventually you. So the same story that built the web built you. You are not a spectator of the cosmos. You are made of it. The very atoms that make up your resting body were once inside stars on the threads of this web. Where else could they have come from? There was nowhere else. Every part of you is borrowed from the pattern and will one day return to it. You are the web, briefly gathered into a person, lying in the warm, thinking about itself. Let us take a slow, imagined journey now, out along that web, the way you might drift along a thought before sleep, not to arrive anywhere, only to travel for a while in the quiet. Begin here, in this room, in the warm and the dark. Rise gently, up through the ceiling, above the house, above the town, until the curve of the earth appears below you, blue and white and turning. Keep rising, past the moon, past the planets, until the whole solar system is a small bright point behind you, and the sun is just one star among the Milky Way's billions. Rise further, up out of the flat disk of our galaxy, until the whole Milky Way spreads out beneath you, a great glowing spiral turning slowly in the dark. And now, keep going, until even the Milky Way shrinks to a single point of light, one galaxy among the thousands of our local neighborhood. And those thousands, as you rise further still, gather themselves into the shape of the web. You begin to see it now, the true structure, the thing itself, long bright filaments of galaxies curving away in every direction, dense glowing knots where the filaments meet, and between them, the great dark voids, vast rounded bubbles of near emptiness, hundreds of millions of light years across, with the galaxies strung around their edges like droplets on a spider's web at dawn. Keep rising, keep drifting outward, until you can see across billions of light years at a glance, until the web spreads out below you like a great luminous foam, filling all of space in every direction, bright threads and dark hollows, on, further than the eye can follow, and somewhere in that immensity, in one direction, toward the constellations of Hercules and the Northern Crown, the galaxies seemed to gather more thickly, crowding together across a span so vast it beggars the mind. The Great Wall itself, or whatever the Great Wall truly is, a brightening in the web, a concentration in the foam, stretching across a tenth of everything you can see. Float there for a while, at that impossible height, and simply look. There is no sound. There is no danger. There is only the web, glowing softly in the dark, the largest pattern there is, with its walls and its voids and its endless bright threads, turning slowly, expanding slowly, as it has for billions of years. You have traveled, in your mind, to the largest scale there is, the scale of the whole cosmic web, and found it beautiful and calm and vast beyond all telling. And down there, somewhere, on one small thread, is a tiny blue world, and a quiet room, and a warm bed, where the part of the universe that can wonder about all of this is lying, softly, letting go of the day. And now, gently, you can begin to drift back down toward it. It is worth spending a quiet while on the people who made all of this visible, because the mapping of the universe is one of the great patient labors of science, and a gentle thing to rest against. For most of human history, the depth of the sky was simply invisible to us. We could see the stars and the faint band of the Milky Way, but we had no way to know how far away anything was, no way to lift the flat scattering of lights off the dome of the sky and give it depth. The universe was a ceiling, not a space. Turning that ceiling into a three-dimensional map, revealing the great web, was the work of generations, and it required both new ideas and enormous patience. Think of Margaret Geller and John Huchra measuring the redshifts of galaxies one at a time, night after night, for years, simply to map a single slice of the sky. There were no shortcuts. Each galaxy had to be found and pointed at, and its faint light gathered and split into a spectrum, and its redshift measured, and its distance calculated, and only then could a single dot be placed on the map. Thousands of galaxies, thousands of nights of careful work to draw one slice of the web, and when they finally saw the Great Wall, and the voids, and the stick figure of galaxies, they were seeing something no human being had ever seen before, the true shape of the universe in depth, revealed for the first time by sheer patient accumulation. And then think of the great surveys that followed, like the Sloan Digital Sky Survey, which took that patient work and multiplied it enormously, using automated telescopes and clever instruments that could measure hundreds of galaxies at once, to map not thousands, but millions of them. Behind that survey stood hundreds of scientists and engineers across many years and many countries, building the instruments, writing the software, checking the data, all so that we could hold at last a detailed map of a large portion of the observable universe. No single person could have done it. It was a shared labor, handed from hand to hand, each contributing a piece to a picture none of them could have drawn alone. And the picture they drew together is the cosmic web, the largest map there is. The discovery of the Great Wall itself came out of that same patient tradition, only using a different kind of marker. Istvan Horvath and his colleagues did not map galaxies directly. They gathered years of records of gamma-ray bursts, the brief, brilliant deaths of distant stars, collected by orbiting telescopes, and they studied how those deaths were distributed across the deep universe. It was, again, slow and careful work, sifting through catalogs, testing for patterns, checking and rechecking. And out of it came the strange and troubling hint of a structure larger than anything allowed. Whether or not the wall proves real, the work that found it was real work, done carefully, by people trying honestly to understand the shape of the cosmos. There is a lesson in all of this that has nothing to do with galaxies, and it is worth carrying gently toward sleep. The largest things in the universe were not revealed in a flash of insight, by a single genius, in a single moment. They were revealed slowly, patiently, by many people, most of whom never met, each adding a little to a picture that took generations to draw. The map of the cosmic web is not the work of one mind or one lifetime. It is a cathedral, built stone by people who knew they would not see it finished, and did the work anyway, because the work was worth doing. And that is how nearly all of our deepest knowledge is made. Not quickly, not alone, but slowly, together, across the years, each of us adding what we can to something larger than ourselves. And it all rests, in the end, on a simple refusal to accept that the sky is only a ceiling. Someone looked up at the flat scattering of lights and was not content to leave it flat. Someone asked how far away each one really was, and then found a way to measure it. Someone looked at a catalog of dying stars and wondered whether their pattern might reveal the hidden shape of the deep universe. That refusal to leave the mystery alone, that gentle, stubborn curiosity, is what lifted the universe off the dome of the sky and gave it depth and structure and a web and walls and voids. It is the most human thing there is, and it is what carried us, in the end, all the way out to the largest structure we have ever glimpsed. Come back now, gently, to the beauty of the thing itself, quite apart from the arguments about its size. Whether or not the Great Wall in Hercules is exactly as large as first thought, the cosmic web is real, and it is one of the most beautiful objects in all of nature. Think of it. The entire universe woven into a single vast pattern, bright threads of galaxies wrapped around dark bubbles of emptiness, the whole thing grown from tiny ripples in the newborn cosmos, amplified by billions of years of patient gravity. It looks, when we map it, like foam, or like the branching of nerve cells in a brain, or like the roots of some enormous tree. The same patterns appear at the largest scale of the universe and in the smallest living things, a strange and lovely echo across all the scales of nature. Sit with that echo for a moment, because it is one of the gentlest wonders there is. The cosmic web, mapped across billions of light years, looks like the branching of nerve cells in a brain. It looks like the roots of a tree. It looks like the threads of a fungus through soil, or the veins of a leaf, or the forking of a river delta from above. Why should the largest thing there is resemble the smallest living things? Not because they are connected. They are not. But because the same simple rules, repeated, tend to make the same shapes. Branching, networks, threads around hollows. Nature reaches for these patterns again and again, at every scale, from the neurons in your head to the galaxies across the sky. There is no plan in it, only the quiet tendency of the universe to rhyme with itself. And there is a deep comfort in that rhyme. The pattern in your own mind, right now, echoes the pattern of the whole cosmos. You are shaped a little like the thing that made you. Let us think, gently, about the far future of the cosmic web, because it is a peaceful long thought, and a fitting one before sleep. The universe is expanding, and that expansion is speeding up, driven by the mysterious thing we call dark energy. And that has a slow and profound consequence for the great web. Over enormous spans of time, the expansion is carrying the galaxies apart, stretching the voids wider, thinning the threads. The great structures that are not tightly bound by gravity, the loose walls and filaments, will slowly be pulled apart as space itself grows between their galaxies. The web will fade over billions upon billions of years as its threads stretch and thin and finally dissolve into the growing dark. The clusters, where gravity has truly bound the galaxies together, will hold. They will remain as isolated islands, each drifting alone in an ever emptier sea, as the space between them grows too fast for any light to bridge. In the very deep future, a civilization living in one such island cluster would look out and see only their own galaxies, with nothing beyond but darkness, the rest of the universe having receded beyond the reach of any telescope. They would have no way of knowing that the great web had ever existed, that there had once been walls and filaments spanning the cosmos, that the sky had once been full of distant galaxies. The web is a feature of this era of the universe, the era we happen to live in, when things are still close enough to see. It will not last forever. There is a strange good fortune in that, worth resting on. We live in the age when the web is visible, when the universe is still young enough and close enough that we can see its great structure, map its threads and voids, and argue about its largest walls. Beings born too late will not have this. The evidence will have faded, carried away by the expansion, and the deep universe will have gone dark. We are among the generations who get to see the cosmic web at all, to know that we live on a thread of a vast and beautiful pattern. That is a gift of timing, of living in this particular chapter of the universe, neither too early, before the web had formed, nor too late, after it has dissolved. We are here at the right moment to see it, and we have used that moment to look, and to map, and to wonder. Let that good fortune settle over you, softly. There is a right time to see the web, and we are living in it. Too early, and it had not yet formed. Too late, and it will have faded, its threads stretched apart by the expanding universe until the deep sky goes dark. But right now, in this chapter of the cosmos, the web is visible. The galaxies are still close enough to see, and to map, and to argue over. Is that not a piece of pure luck? To be born in the one era when the largest pattern there is can still be seen at all? Beings who come long after us will look out and see only darkness beyond their own cluster, with no way to know the web ever existed. But we know. We got to see it. We turned our telescopes on the deep dark and drew the map in the narrow window of time when the map could still be drawn. And we used that window not to look away, but to look harder and to wonder. That is a fine thing for a species to have done with its moment. It is worth letting your mind rest for a while on the great voids of the universe, because they are as much a part of the web as the walls, and there is a strange peace in contemplating such enormous emptiness. When we speak of the cosmic web, we naturally think of the bright parts, the threads and walls of galaxies. But most of the volume of the universe is not thread. It is void, vast, rounded, nearly empty regions, tens and even hundreds of millions of light years across, containing very few galaxies, or in some places almost none at all. The galaxies gather onto the surfaces of these voids, wrapping around them, so that the web is really the thin, bright skin stretched over a mass of enormous dark bubbles. There is one such void in the direction of the constellation Bootes that is famous for its emptiness, a region some 250 million light-years across, in which astronomers, when they first mapped it, found almost nothing at all. It has been called, half in jest, the Great Nothing. And it is so empty that if our own galaxy sat at its center, we would not have known there were other galaxies at all until well into the 20th century, for the nearest ones would have been too faint and too far to see with early telescopes. Imagine that. A civilization arising in the heart of a great void might grow up believing its galaxy was the whole of creation, with nothing but darkness in every direction because its neighbors were simply too far away to be seen. Our own place, on a crowded bright thread with many galaxies near enough to study, is what let us discover the universe at all. Even in this, we have been quietly fortunate. The voids are not truly empty, of course. They hold thin wisps of gas and a scattering of lonely galaxies and the invisible dark matter that threads through everything. But compared to the bright walls, they are deserts, immense and calm and dark, and they are growing. As the universe expands and as matter continues to drain out of the thinning regions and onto the walls, the voids swell, becoming ever larger and ever emptier over the ages. In the far future, they will dominate the universe even more than they do now, vast oceans of dark with the bright walls stretched ever thinner between them. There is a quiet grandeur in that, a universe slowly hollowing out, its emptiness patiently growing, its bright structures thinning toward the dark. It is worth thinking, too, about motion, because nothing in the web is truly still. Everything is moving, slowly, drawn by the gravity of everything else. Our own galaxy is not sitting quietly in space. It is falling, along with thousands of others, toward a great concentration of mass in the direction of the constellations Centaurus and Hydra, a region so massive that it pulls whole superclusters toward it, and which astronomers, with a fine sense of drama, have named the Great Attractor. We are drifting toward it at hundreds of kilometers every second, and have been for the whole of our existence, and will be for a long time to come. We do not feel it. There is no wind of it, no sense of falling. But we are moving all the time, carried along the threads of the web toward the great gatherings of mass, as everything is carried in the slow and silent flow of the cosmos. There is something gently humbling in that, and also something oddly comforting. We think of our world as fixed, as still, as solid ground beneath us. And in a sense it is, for all our daily purposes. But on the largest scale, we are in motion, always, flowing with our galaxy and our whole local group of galaxies toward distant concentrations of mass we cannot even see clearly, part of the vast, slow currents of the cosmic web. Nothing in the universe is truly at rest. Everything is drifting, falling, flowing, on timescales so long that a human life cannot perceive the motion at all. And yet we worked it out. We measured our own motion through the cosmos, our drift toward the Great Attractor, from the tiny shifts it makes in the light around us. Even the slow, secret flow of the web we have learned to read. There is one more idea worth holding gently before we gather the story up, and it concerns time, and the strange way that looking out into the universe is also looking back into the past. When we map the deep universe with gamma-ray bursts, we are not seeing those distant regions as they are now. We are seeing them as they were billions of years ago, when their light and their bursts set out toward us. The Great Wall, if it is real, is not a picture of the universe today. It is a picture of the universe as it was in its youth, an ancient arrangement of matter, carried to us across billions of years by light that has been traveling since before the Earth existed. To look far, in cosmology, is always to look back. Distance and time are woven together, so that the largest map of space is also a map of the deep past. This has a subtle and beautiful consequence. It means we can never see the universe all at one moment. We see the nearby parts as they were recently, and the distant parts as they were long ago, all layered together in a single view, like tree rings, or like the layers of rock in a canyon wall, each depth a different age. The Great Wall lies at a depth that shows us the universe of billions of years ago. What that region looks like now we cannot know and will not know for billions of years more when its present-day light finally reaches us, long after we are gone. So the largest structure we have ever found is, like the great black holes and the distant quasars, partly a ghost, an image of the past, preserved in ancient light, telling us not what the universe is, but what it was. There is a gentle patience required to accept that, and a gentle wonder in it too. We would love to know what the Great Wall looks like now, at this very moment, across the universe. But the universe does not work that way. It hands us only the past, carried on slow light, layer by layer, and asks us to be content with that, to read the history written in the depths, and to accept that the present, out there, is forever hidden from us until its light arrives. In a way, the whole of cosmology is the study of old light, of messages sent long ago and only now arriving. We are readers of an ancient correspondence, piecing together the story of the universe from letters that took billions of years to reach us. And the Great Wall is one of the oldest and largest of those letters, still being read, still being argued over, still not fully understood. Let us widen the view one last time, gently, to the whole of what we have been circling tonight. We are a small species, on a small world, orbiting an ordinary star, on one thread of a web so vast that a single one of its possible walls may span 1/10 of everything we can see. We have been here, as a species able to ask such questions, for the merest flicker of cosmic time. And yet, in that flicker, we have lifted the sky off its dome and given it depth. We have mapped the web. We have measured our own motion through it. We have reached out with the light of dying stars to probe the deepest reaches of the cosmos, and found, out there, a structure that may be the largest thing there is, and had the honesty to admit, we are not yet sure. That is an extraordinary thing for so small and so brief a creature to have done. And it did not make us feel large. That is the quiet paradox at the center of all this, and a fine one to rest on. The more we have learned about the size of the universe, the smaller we have found ourselves to be. A single warm world lost in an ocean of galaxies, on one thread of a web beyond all imagining. And yet the very act of learning it is a kind of greatness, not of size, but of reach. We are tiny, and we have understood, at least in part, the largest structures there are. Both are true, and there is no need to choose between them. You can be a speck, and a speck that comprehends the whole at the same time, and lie here in the dark, holding both, small and vast, together, as you drift towards sleep. It is worth remembering, too, that the Great Wall in Hercules has cousins, other named giants of the deep sky, and knowing a little about them makes the whole picture richer. There is the Sloan Great Wall, mapped in real galaxies, not gamma-ray bursts, stretching across something like 1.5 billion light-years. It is smaller than the Hercules Wall, but it is more solidly established because we can see its galaxies directly. There is a structure called the Giant Arc and another called the Big Ring, both found more recently in the same general part of the sky, both hundreds of millions to billions of light-years across, both raising the same quiet question about how big is too big. And there are vast groupings of quasars strung across billions of light-years that push against the same limit. Each of these has its doubters and its defenders. Each sits somewhere on the spectrum from solidly real to probably a trick of the data. The Sloan Great Wall is widely accepted because it is mapped in ordinary galaxies. The Hercules Wall is more contested because it rests on the sparse light of gamma-ray bursts. The others fall in between. But together, they form a kind of gallery of giants, a collection of structures at the edge of what our rules allow, some certainly real, some uncertain, all of them enormous, and they keep the great question alive. Is the universe truly smooth on the largest scales, as the cosmological principle requires? Or is it lumpier and stranger and grander than our simplest models allow? The Gallery of Giants does not answer the question, but it will not let us forget it either. There is a simple thing worth saying plainly about all of these structures, which is that you could never visit one. You could never stand at the edge of the Hercules wall and look along it, not because it is dangerous, but because it is too large and too far and too spread out. Even if you could travel at the speed of light, it would take you billions of years just to cross a single one of these structures, and by the time you arrived, the universe would have changed beyond recognition, the wall itself stretched and altered by the expansion of space. These are not places in any way a human being could ever experience. They are patterns, visible only from immensely far away, only in maps, only to a mind that can hold billions of light years at once. You cannot go there. You can only know that they are there, and wonder. And perhaps that is fitting, and even a little freeing, as a thought before sleep. There are things in this universe that we can know, but never touch, that we can map, but never visit, that exist for us only as understanding, never as experience. The Great Wall is one of them. We will never send a probe there, never see it up close, never do anything with it at all, except comprehend it, from an unimaginable distance, with the patient reach of the mind. And that is enough. It does not need to be visited to be real, or to be wonderful. It is enough that it is out there, and that we, so small and so far away, have managed to catch a glimpse of it, and to argue honestly about what it is. Some things are ours only to know, and never to hold. And knowing, it turns out, is its own kind of having. Let us slow the mind right down now, with a few small, simple thoughts, before the story closes. The universe is mostly empty. Hold that. Not full. Empty. Great dark voids, with thin, bright walls between them. The galaxies are the walls. The dark is nearly everything. And we live on a bright thread, a crowded one, with neighbors we can see. That is lucky. Many places in the universe have no near neighbors at all, only darkness in every direction. But not here. Here, the sky is full of distant galaxies, and so we could look and learn and map. Our bright thread gave us the universe. A void would have hidden it. Now hold the web itself. One pattern, across all of space. Bright threads, dark hollows, grown from tiny ripples long ago, shaped by gravity over billions of years. It looks like foam. It looks like roots. It looks like the branching in a brain. The same shapes at every scale. Why? Not by plan, just the quiet habit of nature, rhyming with itself. And you are part of it, made of its atoms, riding one of its threads. You are the web, gathered into a person for a little while. Small, yes, but not separate. Never separate. Woven in, all the way down. And somewhere out there, in the direction of the hero and the crown, the galaxies may gather more thickly than they should. A wall, 10 billion light years or more. Too big for the rules? Maybe real. Maybe not. We do not yet know, and that is fine. That is the honest edge of what we know. There is no shame in an open question. There is only the quiet pleasure of one still waiting to be answered. Let it wait. It will keep. It has kept for billions of years. It can keep one more night while you rest. There is a final quiet thought to carry toward sleep. and it is about the privilege of living in a time when questions like this can even be asked. For nearly all of human history, no one knew that other galaxies existed at all. It was only about 100 years ago that we learned the faint smudges in our telescopes were not clouds within our own galaxy, but other galaxies, island universes, unimaginably far away. Everything we have spoken of tonight, the web, the walls, the voids, the great structures at the edge of the cosmos, all of it has been discovered within a single long lifetime. Your great-grandparents were born into a universe that was, as far as anyone knew, just the Milky Way, alone in the dark. You were born into one filled with 100 billion galaxies, woven into a great web, with its largest structures still being argued over. That is a staggering amount of understanding to have arrived in so short a time, and you are among the first human beings ever to hold it. To know that the universe has a shape, to know that it is woven into a web of walls and voids, to be able to lie in the dark and wonder whether the largest structure in the cosmos is truly there or not. None of that was possible for anyone who lived before the last century. It is a brand new inheritance, handed to you across a few short generations by all the patient astronomers who mapped the sky, and you can receive it gently, with a little quiet gratitude, as one of the great gifts of being alive right now, at this particular moment in the long story of our species. So let that gratitude settle alongside the wonder as the day lets go of you. Not only that the great web exists, out there in the dark, but that you get to know it exists, that you were born late enough to be told about the walls and the voids and the giants at the edge of everything. It is a gift, this knowledge, and like any gift, it can simply be received and held for a moment with thanks, and then set down beside the bed so that you can rest. The web will still be there in the morning. The Great Wall will still be waiting, real or not, for someone to settle the question, and you will have slept, held gently on your bright thread, within the largest pattern there is. It is worth taking a slow breath, too, over how gently all of this sits with us in the end, despite its enormous size. A structure 10 billion light years across sounds like it ought to be overwhelming, even frightening. But it is not. It is unimaginably far away. It cannot touch us, cannot reach us, cannot affect our small, warm world in any way at all. It is simply out there, a vast and distant feature of the cosmos, as harmless to you tonight as the most distant mountain is to a sleeping child. The Great Wall, real or not, has never known we exist, and never will. It asks nothing of us. It threatens nothing. It only waits, out at the edge of the visible, to be understood a little better someday, by minds not yet born. And in the meantime, it turns slowly in the dark, and we rest here, safe and small, and utterly untouched by its immensity. There is a real comfort in the distance, when you hold it the right way. The same vastness that makes the Great Wall so hard to comprehend is the vastness that keeps it forever far from us, that keeps every giant of the deep sky at a safe and gentle remove. We live in a quiet, ordinary corner of the web, on a calm thread, far from anything that could disturb us, in an age of the universe mild enough for life to arise and wonder. The great structures are for wondering at, not for fearing, and once the fear is set aside, what remains is only the clean pleasure of knowing such things are out there, and that we, so small, have glimpsed them, and can carry the glimpse gently down into sleep. And perhaps that is the gentlest way to hold the whole of it, as the day slips away. Somewhere out there, in the direction of an old hero and an old crown. The galaxies may be gathered into the largest thing there is, a wall so vast that light needs 10 billion years to cross it. Or perhaps it is a pattern we have read into the sparse light of dying stars, and it will fade as we look closer. We do not yet know. And either way, the cosmic web is real and beautiful, and we are woven into it, a single warm thread among countless others, held gently in the largest pattern the universe has made. That is true tonight, whatever the Great Wall turns out to be. And it is enough to rest upon. It is worth pausing as well on the sheer patience the universe seems to have, because there is something restful in matching a little of it tonight. Every structure we have spoken of took billions of years to form. The web did not appear overnight. It grew slowly, from the faintest ripples, as gravity worked its gentle, ceaseless pull across ages beyond counting. The walls gathered grain by grain, the voids hollowed out over eons. Nothing was rushed. Nothing could be rushed. The largest and most beautiful structures there are were built by the slowest and most patient process imaginable. A quiet gathering that has been underway since the beginning and is not finished even now. There is a lesson in that, if you want one, though it is a soft one, meant for the edge of sleep rather than the sharp light of day. The grandest things are not made quickly. They are made slowly, by small forces acting over long times, without hurry and without rest. The web took the whole age of the universe to weave. Our own understanding of it took generations of patient work. Even you lying here are the result of a slow and patient gathering, atoms drawn together over billions of years into a person able to wonder about the web at all. Slowness is not the enemy of greatness. Very often, it is the only road to it. And tonight, you do not have to hurry toward anything, not even sleep. You can let it come as slowly as it likes, in its own patient time, the way the web itself was made. So let the great pattern turn on in the dark, unhurried, as it always has. Let the walls hold their galaxies, and the voids keep their silence, and the whole vast web drift and expand at its own ancient pace, needing nothing from you, asking nothing of you. You have wondered at it enough for one night. You have followed it out to its largest structure and gently back again. And now your only task, the smallest and easiest task there is to rest, here on your bright and quiet thread, while the largest pattern there is holds you softly through the night. So let us gather the whole of it together now, gently, the way you draw a blanket up at the end of a long day, before we let the story fade into sleep. We began with a simple and beautiful idea, that the universe is not scattered evenly, but woven into a great cosmic web of bright filaments and walls of galaxies wrapped around vast, dark voids, grown over billions of years from tiny ripples in the newborn cosmos. We saw how we slowly mapped that web, lifting the flat sky into 3 dimensions, one redshift at a time, revealing the first Great Wall, and then the Sloan Great Wall, each larger than the last. We met the quiet assumption at the heart of cosmology, the cosmological principle, which says the universe should be smooth on the largest scales, with no structures much bigger than about 1 billion light years, and we followed astronomers as they used gamma-ray bursts, the brightest explosions there are, to probe the deep universe, and found, in the direction of Hercules and the Northern Crown, a clustering that seemed to mark a structure 10 billion light-years across, or more, the Hercules Corona Borealis Great Wall, far larger than the rules allow, the largest structure, if it is real, ever found, And we were honest about that if. We saw why the size is so troubling, a structure many times larger than the cosmological principle should permit, a crack in one of our deepest assumptions. And we saw the real doubts, that the wall was found in the sparse, patchy light of rare gamma-ray bursts, in which chance clusters can appear that are not truly there, so that the wall may be real, or may be a pattern we have read into noise. We found that we do not yet know, and that several other oversized structures keep turning up alongside it, keeping the question stubbornly alive. And we saw that whichever way it turns out, the Great Wall has already done something valuable by making us test our deepest assumptions more carefully than ever before. You do not need to hold any of it now. Let the numbers go, and the names, and the distances. Let the Great Wall, real or not, drift away into the dark. Keep only the one gentle image, if you keep anything at all, of the vast and beautiful web of the universe, its bright threads and dark voids spread across all of space, turning slowly, expanding slowly, with our own small galaxy woven into one of its glowing strands, and you upon it, a single warm point of life, safe within the largest pattern there is, wondering about its farthest walls as you drift toward sleep. So let the whole journey settle now, slowly, the way stillness settles over a room at the very end of the day. We have been a long way tonight, out past the planets, out past the stars, out beyond our whole galaxy, up and out until the entire cosmic web spread below us, all the way to the largest structure anyone has ever glimpsed. It is time to come home now, and to rest. Come back the long way, gently, without any hurry. Back from that impossible height where the web glows softly across all of space. Back down toward one bright thread among the countless threads. Back toward one glowing knot upon that thread, our own small neighborhood of galaxies. Back toward one faint spiral among the thousands, the Milky Way, growing from a point into a great turning wheel of light. Back in through its stars, toward one ordinary star among hundreds of billions. Back to the sun and the small worlds that circle it. Back past the planets, one by one, toward the small blue world third from the sun, turning quietly in the light. Down through the thin, soft layer of its air. Down toward the part of the world where night has fallen, where the lights of the towns glow warm against the dark. Down toward your own country, your own town, your own street. Down toward this building and this room and the quiet bed where you are lying, warm and safe and still. Feel the weight of your body against the bed, held gently by the Earth's own soft gravity. The same force, the very same force, that wove the entire cosmic web over billions of years, that gathered the galaxies onto their bright threads and hollowed out the great voids between them. That vast and patient force, here, in this room, does nothing more than hold you softly in place, exactly where you are meant to be. Feel how still the room is. Feel how little you have to do, right now, in this moment. Nothing needs mapping. Nothing needs solving. Nothing out there in all that vast web needs anything from you tonight. Let your breathing slow and deepen, all on its own, in and out. And with each breath out, let a little more of the day go with it. Let the great numbers go. Let the distances dissolve. Let the web turn on quietly without you, spread across all of space, while you stay here, in the warm, and let go. Feel your shoulders soften. Feel your jaw unclench. Feel your hands grow heavy and your legs grow warm and loose, sinking into the bed. There is a deep peace, if you let yourself feel it, in being one small warm strand of the largest pattern there is, You do not have to be vast to belong. You do not have to span 1 billion light years to matter. You are woven into the web already, made of the same ancient matter as the farthest galaxies, riding the same great structure, part of the same slow turning of everything. And tonight, your part in it is simply to rest, to be a single quiet point of warmth on one thread of the cosmic web, letting the whole immense pattern turn gently on around you, asking nothing of you, holding you softly all the while. You are small, and the web is vast, and both of those are true, and there is no contradiction in them, only a gentle belonging. The largest structure in the universe, whatever it turns out to be, is out there in the dark, turning slowly, expanding slowly, exactly as it has for billions of years, and it will go on turning whether or not you watch it, whether or not you remember a single word of this. You can set it all down now. You can let the great web glow on without you, and let yourself sink, softly, into the near and simple dark of sleep, which asks nothing of you at all. Rest now. Let it all drift. Let yourself be held, softly, by the gentlest thread of the largest pattern there is, and carried down into sleep. Good night.